Okay, so now today we are going to talk about this spherical Bessel functions, right? Now, these spherical Bessel functions actually play important role in scattering problems. Play important role in scattering theory or scattering problems. So you are going to use these uh, spherical Bessel functions when you will do the scattering problem in the quantum mechanics in your second semester. Okay, now I will go back to the previous lectures where we have started with the Helmholtz equation when we separate the Helmholtz equation in spherical coordinates, spherical polar coordinates. And you know that when we separate that Helmholtz equation in spherical polar coordinates in that very lecture, you see that we actually separate them into three different differential equations. And one of the radial equation from there, that particular radial equation was like, if you'll go to the previous lecture notes, you will see that we had one of the equation like r square d2r by dr2 plus twice r dr by dr plus some k square r square minus l into l plus 1 of r is equal to 0. This is one of the equation which we obtain when we actually separate this Helmholtz equation in the spherical polar coordinates, right? Okay, so let me name this as equation 1. So the parameter k actually here is that of the original Helmholtz equation. अगर आपको याद होगा, dou 2 psi plus minus k square psi is equal to 0. So this parameter k जो यहाँ पे है, it is actually from that Helmholtz equation, right? And this L into L plus 1 जो आपका यहाँ पे है, this is a separation constant and is always associated with the angular equation. This is associate this L into L. This is a principal number in the quantum mechanics, and it is associated with the angular equation, and that's why and it is identified by this index L in the angular part. Now, if I will make a particular substitution in this particular equation, that is, I will say that this r, which is this radial part, which is a function of k of r, if I will substitute this z of kr, some variable z, which is a function of kr, by under root of k of r, or we can say if it is an equation in x, then we take it as an under root of x. But since here x is equal to kr, so x square is equal to k square r square, right? So if I am substituting this r, the radial part, by as z by kr into under root of x, or I can say that kr raised to power 1 by 2, or I can say that the under root of k over r. So then this particular equation will be written as, so this, if substituting this r kr into this particular equation, the equation will be like, I can write down this equation as r square. So instead of the r, we have now z, so it will be d2z by dr2 plus twice r, then so not twice, here it will be r dz by dr plus k square r square minus L plus 1 by 2 whole square into Z will be equal to 0. So by making this substitution, by substituting this RKR into this particular differential, instead of this R, so this particular equation will take the form like this. Okay. Now this equation is what we call as a Bessel equation, but it is a Bessel equation of order L. This is a Bessel equation of order L plus 1 by 2, half integral value L plus 1 by 2. Now the general solution to this particular, because now since when we take any differential equation and a dependent variable y, so we talk the solution will be in the form of a y, so that is y is equal to something like this. Now it is a differential equation in z, so the general solution will be as like z of kr, because z is a function of kr. So this is a linear combination of the general solution to this equation general solution, that is ZKR, is a linear combination of is a linear combination of this j half j1 by 2 sorry jl plus 1 by 2, because jl plus 1 by 2 of x, and y न्यूमान फंक्शन जो बेसल फंक्शन ऑफ सेकंड सॉल्यूशन होता है l plus 1 by 2 of x. So that will be a linear combination of these two solutions. Now, you know that when we take a general Bessel second order differential equation, and we don't know how we know how to write down the solution to that particular differential equation, then we say that the solution to that particular differential will be a linear combination of uh, of two different solutions, jn of x plus b yn of x. Now, instead of n, and here we have l plus 1 by 2, so that's why we call them as a, I will just come to this in a while. So I will take, so the solution to this particular differential equation, I'm not going to find out the solution to solution here. I will write down the solution here. I will tell you the importance of the spherical Bessel functions. So I'm saying that since the solution to this particular differential equation will be in the form of zkr, and it is a linear combination of the solution, because it is a second order second order differential equation, so it will have a two linearly independent solution. So that solution will be actually the linear combination of these two solutions. I will just write down these two solutions in a while, but just I'm just telling you the importance actually, where does this arise and how actually we can have the solution. So which means that we can write down the this RKR, because this ZKR we are actually defining it in terms of an RKR. So RKR is defined in terms of ZKR. So I will say that we can write RKR. So we can write this R, radial part of which is a function of KR. So K is some parameter that is taken from that Helmholtz equation, and R is actually the some variable here. RKR in terms of these Bessel functions, in these Bessel functions of half integral order, half integral order, half integral order. Okay, so that means we will write down this R, which is defined here, because this is a differential equation. We can write down this in terms of a Bessel functions of half integral order. So you know that what are the Bessel functions of the half integral order? J1 by 2 of x, J3 by 2 of x, so on and so forth. We have obtained all these values from the original Bessel differential equations. Now it's this spherical Bessel functions is not same as that of the Bessel function, जो normal Bessel function हमारे पास हैं, but they are related. How they are related, that I'm going to show you. So this RKR I can write down in terms of this Bessel function like. So I will write down, since as I said, this RKR in terms of these Bessel functions can be written as RK of R, that is given by some constant C by under root of K of R. This is a normalizer factor actually here, J L plus 1 by 2 of X. Sorry, not X, this is KR, because it's a function of KR, J half of this. Now, as I said, कि this R part जो है आपका, इसमें it describes the radial function in spherical coordinates. So when I separate the Helmholtz equation in the spherical polar coordinates, so this R part actually describes the radial function in spherical coordinates. So that's why we term them as the spherical Bessel function. That is the reason we call them as a spherical Bessel functions. Fine. Now I will consider two this spherical Bessel functions, because when I consider the Bessel functions of this type, this is if you'll compare this particular differential equation with the original Bessel differential equation, जो Bessel differential equation है, you will see there we have this factor, वहाँ पे हमारे पास x square minus n square है. So instead of n we have here we have here L into L plus 1. This is a principal quantum number in the quantum mechanics. So I will write down those the spherical Bessel functions in terms of in terms of the original Bessel functions. So the spherical Bessel function, and you know that as I was saying, this Bessel function, since it is a second order differential equation and it has the two linearly independent solutions, one is Jn of x and then Yn is one and Yn of x. We call this a Bessel function of first kind, and we call this as a Bessel function of second kind. Also we call this as a Neumann function, जिनको हम बोलते हैं. So the spherical Bessel function and the Neumann functions are defined as spherical Bessel and spherical this Neumann functions are defined as. How we actually define them? So this is represented by Jn of x. This is a small Jn of x that will actually distinguish it from the normal Jnx. So it is always given by under root of pi by 2x. This is a normalizing factor. J of n plus 1 by 2 of x. Yani we define the spherical Bessel function in terms of this Bessel function, spherical Bessel function in terms of this Bessel function. Okay, and you know that the second function you have yn of x, that is given by under root of pi by 2x, the yn plus 1 by 2 of x. Now, if you'll go to the previous lectures, यहाँ पे हमने Bessel function start किया था, you can see there we have defined this n 1 by 2. We can take the different values of n like 0, 1, 2, 3, 4. I will just obtain some of the Bessel functions. Yani root is this j0 x y and x, but I will do this after some time. Not so here it's a small y n of x. So we are actually defining these Bessel functions, spherical Bessel and Neumann functions, where this n can take the values like 0, 1, 2, 3, so on. Okay, and I can so these are actually the solutions to. They are actually the solutions of the differential equation. Which differential equation? So these are solutions to, these are solutions of differential equation. These are solutions of the differential equation. This x square d2r by I can take it as a dx2, or I can say that the dr2. So let me write first as dx2 plus, because I'm defining it in terms of an x. So I will say that x square d2r by dx2 plus 2x dr by dx plus x square minus this L into L plus 1 into R is equal to 0. So these two solutions are the two linearly independent solutions to this particular differential equation. Okay, again you can name these as equations. So name this as equation, उसको मैंने equation 1 दिया था शायद 1. Okay, so you can now name this as this equation as equation 2 and this equation as equation 3, because I'm going to use these equations later on. Okay, now you know that when we do this Helmholtz equation, when we separate that in the spherical polar coordinates, so we get this relation. So actually the spherical Bessel and Neumann function, the first part, this part is just an introductory part about the spherical Bessel functions. Now I am starting from this particular point. यहाँ पे आप थोड़ा concentrate करिए इसमें, that the spherical functions, Bessel functions are defined in terms of these Bessel functions, and these are actually the solutions to this kind of a differential equation, this kind of a Bessel differential equation. Okay, so now I'm saying that when we take the Helmholtz equation into the consideration, and when we separate that into the spherical polar coordinates, we get an equation like r square d2r by dr2, okay, plus this 2r into dr by dr plus this k square r square minus lambda into r is equal to 0. And this is equation 4. Okay, so when I separate the Helmholtz equation into the spherical form, the radial equation which I get from that is this particular equation. Now this particular equation, that is equation 4, is identical with this equation. This is identical with this particular equation. This is the different equation, this is it, but they are identical with what is the identity between these two? So they are identical. These two equations are identical with x is equal to kr. So if you are going to use x is equal to kr in this particular equation, so this will become the same, and lambda is equal to L into L plus 1. So these two equations, that is equation 3 and equation 4, are identical. Now again, as I was saying in the introductory part, I can just substitute this R of x, R which is a function of x, into Z of x divided by अंडर रूट ऑफ एक्स और एक्स रेज्ड पावर अंडर रूट ऑफ एक्स. अभी जो इंट्रोडक्टरी पार्ट में आपसे बोल रहा था, so if I will substitute r of x, z of x into under root of x in this particular equation, then the equation can be, this particular equation can be transformed into a Bessel equation of order L plus 1 by 2. This particular equation can be transformed into a, or this Bessel differential equation of order. So the equation, then the equation 4 can be transformed into Bessel's equation of order L plus 1 by 2. Okay, and the particular this will be a Bessel equation of order L plus 1 by 2. Okay, then what will be this equation like? So this particular equation will now then become like x square d2z by dx2 plus x into dz by dx plus this k square x square, this will be now x square minus L plus 1 by 2 square into z will be equal to 0. This is again a repetition of these things जो मैं यहाँ पे आपसे बोल रहा था. So I was just in the introductory part, I just take into the consideration this Helmholtz equation. Then I told you that making this substitution, this is again the same thing, but I am now starting afresh. So after the introductory part, I am just starting from this particular point, this thing. So you have to concentrate actually. Your lecture starts from this particular. When we talk about spherical Bessel functions, we are actually starting. This is, I was giving you some, because you already have gone through this type of an equation when we were doing the Helmholtz equation and all that. Here I am using the another different symbols. That's why I'm repeating it for this case. So when you are going to make in this particular differential equation, when you are making this substitution, when Rx is written in terms of some other variable z, which is also a function, this is a radial part. So this particular equation will be transformed into a Bessel equation of order L plus 1 by 2. Okay, so now since this is a Bessel equation of order L plus 1 by 2, earlier we used it to have the Bessel equations of order n or n minus n. Okay, so here what could be the solution? So J, okay, so since this particular differential equation, since J L plus 1 by 2 of x and J L, sorry, y, not yeah, I can see, let me write this as y, L plus 1 by 2 of x are actually the two linearly independent solutions to this particular differential equation. Okay, now the normalizer factor, so J L half and this y L half are the two independent solutions to this second order differential equation. Okay, usually when I say that I have a differential equation of order L, so you will say that it will have the two independent solutions of order L, but this particular differential equation here is a differential equation of order L plus 1 by 2. So J L plus 1 by 2 and Y L plus 1 2 will be the two linearly independent solutions to this particular equation. Now coming back to this equation second, जहाँ पे मैंने J n under root of pi by 2 x लिया था. Now this under root pi by 2 जो यहाँ पे है, under root pi by 2 here in equation under root pi by 2 in equation 2, that is which is a normalized fact. This is a normalization factor. And has been chosen to ensure that this J0 of x, for n equal to not this J0 of x and this Y0 of x has the form sine of x by x and minus cos of x by x. I will just explain this in a while, how this is equal to this particular. So we are actually choosing this normalizer factor so that the this j0 of x, then if the Bessel spherical Bessel function of what is 0 will take the form like sin x by x and cos of x by x. I will obtain these values just in a while. Okay, so now as I was saying, this jn of x, this jn of x and yn of x, they are related to they are related to they are related to Bessel function. They are not same, but they are related to. Now you can see this is a Bessel function of first kind and this is a Bessel function of second kind, जिसको हम Newman function. So this J and X, spherical Bessel function and spherical Newman function, they are related to what? They are related to Bessel and Newman functions. Most of their properties can be followed from the properties of this J and X, Bessel function of first kind as well as the Newman functions. And you, if you remember, we actually represent them by as J n of x. This is a Bessel function. या हम इसको J nu of x से भी represent करते हैं. And this is y n of x. So Newman function or y nu of x. So the properties of this J n of x, they are related, and this y n of x, they are actually, they can be directly followed from the properties of this. Whatever the properties they follow, it will follow the same properties. What I mean by this, so since you know that how we write down from the power series expansion of j and x, jn of x, the solution to from the power series, we write down the solution जिनको हम Bessel function of first kind. So we write the solution as under root of pi by 2x, right? Summation, forget about this normalization, you are starting there from this point, summation s running from 0 to infinity minus 1 raised to power s, then 1 divided by s factorial gamma of n plus s, gamma of n plus s plus 1, right? वहां पे आप gamma of n plus s plus 1 लिखते हैं, but here n is equal to n plus 1, sorry, n is equal to n plus 1 by 2. Yeah, L is equal to L plus 1 by 2 में half of this order. So this will now gamma of n plus s plus 1 will become gamma of n plus 1 by 2 plus s plus 1. So it will be gamma of n plus s plus 1 by 2, and this will become 3 by 2. So the solution to this j and x will be the minus 1 raised to power gamma n plus s plus 3 by 2. Then we have x raised to x by 2, वहां पे हमारे पास x by 2 raised power n plus 2s है, right? So n equal to 1 by 2, so what will this become? It will become now x raised to power, when n is equal to n plus 1 by 2, it will become 2s plus n plus 1 by 2. ठीक है? Try to understand this. जहाँ पे हम the Bessel function जब j n s लिखते हैं, वहाँ पे हम simply summation sum s running from 0 to infinity minus 1 raised to power s 1 divided by s factorial gamma of n plus s plus 1 x by 2 raised to power 2s plus n, या n plus 2s लिखते हैं. Now if you substitute n is equal to n plus 1 by 2 in this particular equation, so this equation will be like s plus n plus s plus 3 by 2. Okay. So if so now I will use the relation, I will use the result here, gamma function. So gamma of n plus 1 by 2, gamma of n plus 1 by 2 is always given by under root of pi by 2 raised to power n, then 2n plus 1 double factorial. So what I mean by the, where n can take the values like 0 1 2 so on. So what is this 2n double factorial? This where this 2n plus 1 double factorial will always take the 1 3 5. So n can take the different values like n is equal to 0 1, n is equal to 2n, sorry, 2n minus 1, 2n minus 1, 2n minus 1. So for n equal to 1 it will be, for n equal to 0 minus 1 वाला double factorial हम देखते नहीं, we are starting from 2, sorry 1. So n can take the values 0 1, 0 भी है but that is 0 factorial, that will again become 1. So we can take the values 1, 1. So for example, for 2 minus 1 is 1, 2 2s are 4, minus 1 is 3, 2 3s are 6, minus 1 is 5, so on. It can go up to the 2n minus 1 values. So this is the values of this. Now we know that this jn of x, jn of x is given by some summation s running from 0 to infinity, जो मैं यहाँ पे आपसे कह रहा था, minus sorry, okay, some I will write minus 1 raised to power s, minus 1 raised to power s, okay, 1 divided by this is s factorial, then I will have s factorial, this gamma function. When I'm going to use this gamma function, gamma of n plus 3 by 2, it will be like 2l plus 2s plus 1, then x raised to power l plus 2s. This particular equation will now become jn of x. This is not a capital, this is a small jn of x, jn of x. Okay, now this jn of x, as x will tend to 0, x not 0, but as x will tend to x 0, so this jn of x will be equal to, okay, substitute s is equal to 0, this will be 0 factorial, this will be 2l, s will be 0 here, it will be simply this jn of x will be uh, x raised to power l, because 2s, s will become 0 for s is equal to 0, divided by 2l plus 1, 2l plus 1, यहाँ पे double factorial है, 2l plus 1 double factorial. So this is what we will get the value for this jn of x. Okay, now when you are going to plot this jn of x at origin, it is finite, यानी at origin it will be finite. For example, अभी मैं आपको कहूँ, अभी I will just find this j0 of x. जब हम ये j0 of x find करेंगे, it will be like sin x by x, जिसको हम सिंक फंक्शन बोलते हैं. तो अगर आपको याद होगा डिफ्रैक्शन पैटर्न जब हम फाइंड करते हैं, you know that how we find out the diffraction pattern like this. This is the diffraction pattern. So I will just consider this. So at this 0 point, this will take a this function will take a finite value, right? So that means it will be like this, then this, then this, then this. So this will have a form like this if I'm going to take only the thing on the positive hand side. Otherwise the function is like, yeah, ऐसे है आपका diffraction pattern sin x by x. I will just find the sin x by x from that equation. So you need to remember that origin we have this equal to 0. At origin we have this jn of x equal to 0. Also, if you remember from जब हम Bessel function में कुछ exercise कर रहे थे, we have obtained that this jn of x या j nu of x. No, I'm using n, so I will use this in jn here. Jn of x is always given by under root of 2 by pi x cos of this x minus n pi by 4 minus pi by n pi by 2 minus pi by 4. Go through that exercise, we have obtained these values. And also this n, or I will write down this as yn of x. Yn of x is given by under root of 2 of pi x, then sine of x minus n pi by 2 minus pi by 4 from the previous cases. So on now use from these equations, it will follow that this jn of x जो मैं अभी लिख रहा था, from these equations, it follows that this jn of x, is always given by 1 by x sine of x minus l pi by 2. So it will take the different values of the l, and this yn of x in a spherical Bessel function, it is always given by minus 1 by x cos of x minus l pi by 2. So as x will tend to infinity, so this yn of x will be infinite at x is equal to 0, but as x tends to infinity, but this jn x will be finite at x is equal to 0 also. So this is what we call as a spherical Bessel functions. So Bessel function, so also the solution to this Bessel function, some of the books have written it as the solution is like given by jn of x is equal to minus x raised to power n 1 by x d by dx raised to power n sine of x by x. Okay, you forget about this. If you go, some of the books have given the solution to this this problem, but we will try to obtain the solution in terms of a Bessel function which we already know. So what are those functions? For example, let us come go back to this जो मैंने अभी आपसे कहा था. uh, let me go back. Let me go there. Since I say that this jn of x is equal to under root of pi by 2x, under root of pi by 2x, j n plus 1 by 2, n plus 1 by 2 of x. Okay, so I can obtain the values. Now I already know, agar we have obtained the values of j1 by 2, j3 by 2, right? So what is the value if you remember j1 by 2, j1 by 2 का वैल्यू अगर आपको याद होगा, j1 by 2 अगर आपको याद होगा वैल्यू, it is always given by j half of integral, it is always given by 2 by pi x, 2 by pi x sine of x. We have obtained this value in an exercise. Similarly, we have also find out the j3 by 2. Okay, so j for n equal to 0, what will this now equation become? So for n equal to 0, this j0 of x will be now equal to under root of pi by 2x into under root of j. So n equal to 0, it will be j half. Instead of j half, I will have 2 by pi x into sine of x. Okay, so what this under root 2 and under root 2, pi and pi will cancel out. We will have the sine x by x. Similarly, I can find out the other j1 of x. So the j1 of x के बाद क्या होगा? It will be j3 by 2. j3 by 2 का value आपको पता है. So you just find out j1 of x also. Sorry, this j1 of x. So for that you will just substitute n equal to 1. It will be just go through the notes. You will find out j3 by 2 of x का भी हमने value find किया है. So just find out from this j0 of x मैंने किया है, j1 of x आप find करिएगा क्या है. Similarly, in the for the other case जो yn of x मैं बोल रहा था, yn of x is given by under root of pi by 2x. Okay, then yn plus 1 by 2 of x. So from the Newman function, you know that this yn half is given by minus, it is given by minus under root 2 by pi x into cos of x. So for n equal to 0, from this equation n equal to 0, this y0 of x will now be equal to under root pi by 2x. Okay, this is not actually you have to conclude. I was supposed to conclude here. So these are the Bessel functions and we represent them by these functions. This is some extra information I am giving you how we can obtain these spherical Bessel functions in terms of the Bessel functions and the Newman functions, Bessel functions of first kind. Okay, so this will be now this minus sign, it will be now under root 2 by pi x again into cos of x. So its value will be cos of x by x minus cos of x by x. Fine. Okay, so this is j0 of x is given by sine x by this x, and j0 of x is given by this thing. So this is the way we actually obtain these values from these are the spherical. So the spherical Bessel functions are actually they are different from the Bessel function and the Newman functions, but they are related. How they are related? They are related by this spherical. So now these spherical Bessel functions are actually important in, as I was saying, the scattering theory, because वहाँ पे जब हम we will be having the spherical symmetry of the particular problem. Okay, I hope you have understood it. Now if you have any question or any doubt regarding this what I had said, you can just tell me. I will just give you more explanation. Is there any question?
No, sir.
Okay,